Hello everyone, myself Krishna Pranav. I am from IT section first semester and today I am here to present on analysis of complex RLC circuits. Objectives. The primary purpose of this project is to explore the dynamic behavior of the complex RLC circuits which it is when it is exposed to an alternating current AC supply. The objectives include to study how resistors, inductors and capacitors react when combined in series, parallel arrangements, their mathematical and physical behaviors interview, creating unique responses that differ from simple circuits to determine total impedance by applying complex algebra. The goal is to understand how real and reactive components shape the magnitude and phase of the current, to observe and analyze resonance phenomena, where the circuit either magnifies or suppresses certain frequencies. Resonance plays a crucial role in tuning, filtering, and signal selection. To analyze transient and steady state behaviors, the circuit reacts differently at the initial application of AC transient compared to long term operation steady state. To validate results through simulation and theoretical calculations, ensuring that analytical predictions align with practical or software based observations. To understand the real world relevance of RLC circuits in communication systems, audio systems, power electronics, filters, and oscillators. These objectives together help build a structured understanding of how energy moves, transforms, and resonates within a RLC environment. The requirements. Requirements are of hardware requirements as well as software requirements. Hardware requirements are resistors, inductors, capacitors, function generator, oscilloscope, multimeter, connection wires, and software requirements are MIT lab, graphic, graphing tools, etc. Resistors. Resistors manage the flow of current and convert electrical energy into heat. In RLC circuits, they prevent excessive oscillations and determine the damping factor. Inductors. Inductors store energy in magnetic fields and oppose current in changes in current. They add positive resistance, influencing current resonance and phase shift. Capacitors. Capacitors store energy in electric fields and oppose changes in voltage. They contribute negative reactance, balancing the inductor at resonance. Function generator produces AC signals of various frequencies to observe frequency dependent behavior. Oscilloscope displays waveforms, phase differences, resonance peaks, and transient responses. Multimeter measures RMS voltage, current, and component values. Connection wires used for constructing the physical circuit. Software requirements. These platforms simulate circuits, allowing frequency sweeps, board plots, phase plots, and transient analysis. Graphing tools used to plot frequency responsive curves and impedance graphs. Together, the hardware and software create a holistic environment for complete, accurate circuit analysis. Technology and methodology. First, technology. AC circuit theory. Understanding sinusoidal steady state analysis. Complex numbers and phasor algebra. Converts differential equations into manage- uh, manageable algebraic expressions. Impedance calculations. Allow analysis without solving time dependent equations. Frequency response analysis studies how circuit behave across various frequencies. Simultaneous technology visualizes waveforms and validates manual calculations. Methodology circuit identification recognize the structure of the RLC network like it is series or parallel or both combined. Derivation using Kirchhoff's laws, which are KVL and KCL. Conversion of impedance domain. ZR equal to ZL equal to J omega L, ZC equal to 1 by J omega C. This transforms the circuit into a purely algebraic model. Calculation of total impedance. Depending on the configuration, impedances are added in series or parallel. Frequency sweep and resonance analysis. Vary frequency to find resonance frequency, bandwidth, quality factor, peak responses. Simultaneous validations. Software simultaneous confirm theoretical expectations and highlight practical deviations. Documentation. Recording observations, graphs, explanations, and comparing theory versus simulation. This structured approach ensures that no layer of analysis is left unexplored. Block diagram. AC source, RLC circuit, then measuring instruments, and then analysis. Explanation. A complex RLC circuit is one where resistors, inductors, as well as capacitors are arranged in series parallel combination instead of a single simple loop. Resistor consumes energy, inductor temporarily stores energy into magnetic field, capacitor stores energy in electric fields. The circuit may amplify certain frequencies and mute others, making it essential in radio tuning, signal shaping, and filtering. Impedance interaction. Resistors contribute real impedance. Inductors and capacitors contribute imaginary impedance. Their balance determines total circuit behavior. Phase angle variation. The circuit can behave like a resistive circuit, a capacitive circuit, and an inductive circuit. The shifting of phase angle between voltage and current creates the foundation for AC power theory. Resonance phenomena. At resonance, inductive and capacitive reactance cancel out. Omega naught equal to 1 by root over LC. This leads to either maximum current series or minimum current parallel. The circuit becomes either remarkably conductive or remarkably selective. Transient behavior. When AC is applied, the circuit experiences momentary oscillations as energy bounces between L and C until resistance damps it. Steady state behavior. After transient fade, sinusoidal responses dominate, making the circuit predictable. The RLC circuit is essentially a playground where energy flows between electric and magnetic fields while resistance quietly tames the motion. In this diagram, R is resistor, L is inductor, and C is capacitor. V is an AC input supply, I is circuit current, and Z is overall impedance. How, how will it help us? Helps understanding frequency dependent behavior, vital for engineering and electronics. Offers insight into filter design, low passes, high pass, band stop, etc. Assist in building oscillators, communication circuits, and signal conditioners. Strengthens fundamental required in control system, embedded electronics, and power networks. Helps diagnose issues like resonance, overcurrent, or unwanted oscillations in AC system. Then merits and demerits. Merits: predictable behavior, essential for tuning, can achieve very sharp resonance used in power conditioning, audio circuits, and RF technology. Demerits: inductors are physically large and expensive. Sensitive: high resonance circuits voltage can damage components. More more complex to analyze compared to simple resistive networks. Result: the analysis reveals impedance drops to minimum at series resonance. Phase angle becomes zero at resonance. For parallel resonance, impedance peaks dramatically. Experimental or sinusoidal waveform shows increased amplitude at resonance. Frequency sweep produces well-defined resonance curves. The results validate the theoretical formulae and highlight real-world derivations due to parasitic elements and losses. The frequency response curve shows selective amplification near resonance and attention outside it. Conclusion: complex RLC circuits are foundational to electronics and communication technologies. Their ability to control and script signals make them indispensable in radios, televisions, power circuits, and digital communication systems. Understanding resonance, impedance, and phase behavior equips engineers with the tools needed to design stable and efficient systems. The interplay between resistance, inductance, and capacitance paints a dramatic portrait of electrical energy, sometimes steady, sometimes oscillatory, always informative. The analysis brings clarity to how electrical energy dances through components, sometimes calm, sometimes dramatic, resonant. These are the differences. Thank you.